Good morning, dear students. Welcome to this session on pre-stressed concrete. We are talking about the Unit 3 loss of pre-stress. So, last few sessions we have completed loss of pre-stress due to elastic shortening, and the second one being due to shrinkage of concrete. Now, even in the very last session, we have completed the loss of stress due to creep of concrete. Let us just recall once again. So, creep is a phenomena which we talked about already in Unit 1 of your syllabus, the properties of concrete. So, when you have a constant stress on any member, the strain that it will develop over a period of time is called the creep. Okay, that strain value is called creep strain. Okay, and the total strain value in its lifetime of a member is going to be total creep strain or ultimate creep strain. Okay, right. So you can measure the creep strain at any point of time in its lifetime of a member. Okay, so when you have a constant stress acting on the concrete, the strain that it experience will be called as creep. Okay, right. So the creep reduces the stress in steel. Reason, concrete is going to be compressed, hence the steel is also going to be reducing its length. Means the compressive strain will happen along with concrete into the steel also, so that will cause the loss of stress. So there are two methods. One is called ultimate creep strain method, where if you know the value of ultimate creep strain per unit stress, that will be multiplied with the Young's modulus, will give you no loss of stress per unit stress. And if you multiply with the total stress value in the concrete at the level of steel, that will give you the loss of stress. Okay, so if you multiply these two, strain and Young's modulus, you will have the stress value. So that stress value will be per unit stress. For 1 unit of stress applied, that will be multiplied with this the total stress value in the concrete at the level of steel. So that will give you the loss of stress in steel due to creep of concrete with the ultimate creep strain method. Okay, that will be the one such method. The other one is uh, creep coefficient method. Creep coefficient method. The creep coefficient method is with the use of creep coefficient value, which is phi. So phi is defined as ratio of creep strain to elastic strain. So the creep strain means the value of strain at any point of time that you measure due to creep. Okay. Elastic strain is the one which you measure in the concrete with at the transfer. When you transfer the stress immediately, what is the strain value? Okay, and alpha being modular ratio. So the creep coefficient is defined as creep strain divided by elastic strain. So creep strain is equal to phi into elastic strain. and elastic strain may be replaced as stress by Young's modulus. Okay, so that will be the formula that you can develop for creep strain value. So creep strain is now written as phi into stress by Young's modulus in concrete. So again, this strain multiplied by Young's modulus of steel will give you stress in steel. Okay. So this multiplied by ES will be the loss of stress in steel. Okay. So that is this step. Okay. And anyhow, ES divided by EC is alpha, which is modular ratio. So creep coefficient, modular ratio, and FC being the stress in concrete at the level of steel. Okay, so this is creep coefficient method. So either you can use creep coefficient value or ultimate creep strain method. Any one of the methods you can use. And this was the example which we have seen, where you can see that the creep strain value, ultimate creep strain value is given to you 41 into 10 power minus 6. As it is strain value, there won't be any units, but some number mm by mm gets cancels per 1 unit stress. So 41 into 10 power minus 6 is the strain value, ultimate creep strain value. And creep coefficient is given as 1.6. Okay. So stress in concrete at the level of steel is found from the given data. Okay. And then ultimate creep strain method we have used and got the value. And even creep coefficient method also being used and got the value. And I told you that the procedure can also be done with the codal procedure also. So go for 625 IS 625 class 625 and use the values and formulae given in IS code. Okay, whatever values, for example, this creep coefficient 1.6, you can read the exact value from the IS code. Okay, not only from the given data. 2012 IS 2012, you can read from the IS code. Okay, even the loss of stress at particular point of time also can be found, not from the so the creep strain shall be uh, taken from the IS code, either the value, if the sufficient data is not available from the experiment, you can also use the tabular values given in IS code. Okay. Now coming to the loss of pre-stress due to relaxation of steel. So this relaxation of steel is a direct value. You can read it from the table. There won't be any formula or nothing. So the loss is just directly table value taken from a table given in 19.5.2.3. Okay. Say for example, if the characteristic strength of steel is 1000, okay, 1000 megapascal, and if the initial stress is just a second, just if the initial stress is 1000, so characteristic strength of the steel is 1000 megapascal. Say if initial jacking of the tendons is up to say half the value, like zero point 0.5 times of 1000, say 500 megapascal, then you can read it to uh, zero, like there won't be any losses at all due to relaxation. Okay, and if it is 600 megapascal, if it is initial stress, then you shall see that there will be uh, a loss of 3%. Okay, in the loss. Okay, it is in terms of percentage. You have to read it as percentage. So 3% is lost, like 1000 into 3 by 100. Okay, so that is how you have to read the loss. Okay, so 30 megapascal is lost from 1000 because of relaxation. Relaxation loss is also time dependent. Okay, over the time, as the steel is under constant stress, there will be strain, extra strain in the steel. That is what is called relaxation. Okay, so just a blind example is like when you tie a wire tightly to the 2 points, uh, uh, very much tightly and no sag at all. Don't observe any sag at all. So the it seems to be the cable is very straight. Now, after some time, like maybe 1 year or 2 years or 3 years, the slowly sag appears, which means you have not increased the stress, you have applied constant stress. Okay, but the strain increased. That is what is called relaxation phenomena. So if the stress is high, loss is also high. So if your initial stress is 800, 80%, the loss is also 8%. Okay, so this is how relaxation loss will be calculated. Okay, it's directly as percentage. Okay, you don't need any calculation, no formula, nothing. Now let us see loss of pre-stress due to anchorage slip. Okay, the fifth loss in a row. Like we started with elastic shortening, the first one, shrinkage loss, second one, and then creep, the third one. Now the fourth one was to talk about relaxation loss, and the fifth one is now anchorage slip. Okay, this is very simple based on the concept of axial stress. Okay, axial strain, the axial deformation. Okay, any loss of pre-stress which may occur due to slip of wires during anchoring or due to the strain of anchorage shall be allowed for in the design. Okay, the magnitude of loss of stress due to slip in anchorage is computed as like this. It's a simple formula. So delta, we read it as slip of anchorage. Okay. Now L is the length of the cable and cross-sectional area, modulus of elastic steel, and pre-stressing force likewise. Okay. So every member uh, has got a duct provided for inserting the cable. So this is a duct. Imagine you have got a cable inside this, and you are going to provide some anchorage device to hold this wire. So when you provide, say for example, there is a cable and gripping it. So when you are releasing the tendon from the jock and the to hold the uh, tendon or cable, the device that you are using is called anchorage device. So it has got some slip while it is going to hold the wire once it is released from the jock. That is what is exactly called slip in anchorage. So it is simply like no, delta is equal to PL by AE, which is a well-known formula for no, axial strain to calculate axial deformation. It is from a very simple basic concept like Young's modulus is stress by strain, where replace for stress, which is P by A, and strain is like change in length by original length. Now you can rearrange like EL by A delta. Now what you want is the delta, that is deformation, axial deformation. So E comes down, PL by AE is the deformation value. That is like loss of stress if you want. It is P by A is the stress value. This is the loss of stress that is uh, proportional to this delta value. So stress is equal to, now this delta goes to numerator. So E into delta by L. So that is what is F value, which is loss of stress. So it is like E into E in the sense Young's modulus of steel delta by L. Again, you see delta by L is strain only. So strain into Young's modulus is again stress. This is all of very basic relations to calculate the loss due to anchorage slip. It is very simple. E into, which is Young's modulus of steel, into the slip value, how much is the slip in anchorage divided by length of the cable. Okay, right? So we'll see one example. A concrete beam is post tension. I forgot to tell you that the slip in anchorage loss due to slip in anchorage is only for post tension members, because we don't have any anchorage device in pre-tension member. So this loss is only for post tensioned members. Okay, right. So a concrete beam is post tensioned by cable carrying an initial stress of 1000. The slip at the jacking end was observed to be 5 mm. So 5 mm is moved by the tendon uh, when it is released from the jock and anchored. Once the anchorage device has come into picture, so that slip is 5 mm and never happens again. So this will be holding the tendon till its life of the member. So at that position, once the 5 mm has occurred, slipping is occurred. Okay, the modulus of elasticity of steel is given. Estimate the percentage loss of stress due to anchorage slip if the length of the beam is 30 meters, and in case of the other case 3 meters, just to compare. So loss of stress due to anchorage slip is simply strain into delta by L. So I mean Young's modulus into delta by L. Young's modulus value 210 into 10 cube into 5 divided by 5 mm. So in meters, 5 divided by no, I mean 1000 meters. So 30 meters is the length of the cable, nothing but the beam. So in this case, the length of the beam and length of the cable is taken as same. Okay. So either you can convert the 5 mm into meters or 30 meters into mm, both are same. Okay, because the units that the Young's modulus is having will be the same units of stress. So 210 kilonewtons converted to newtons, 10 cube into 5 mm divided by 30 meters, 30 into 1000 mm. So that is coming around 35 Newton per mm square. So percentage of loss, the loss of stress divided by initial stress is 1000, 3.5%. Now for a 3 meter long beam, so Young's modulus, the slip value and the length of the beam, 3. So this is 350 Newton per mm square and the percentage is 35%. So anchorage slip loss is now inversely proportional to the length. The length is very high, loss will be less. If the length is very small, the loss will be very high. Okay, inversely proportional. Okay, the loss of stress due to anchorage slip is inversely proportional to length of the member, and it is directly proportional to the slip value. The slip is high, the loss is also high. Okay, so this is about uh, you know uh, the loss of stress due to anchorage slip. As I told you, loss due to relaxation is directly a percentage reading from the IS code. Remember this clause 19.5.2.3. Okay, I'll show you that also. Open your IS code. Just to feel comfortable whether it is available in the IS code or not. So just to make you to feel comfortable with the reading IS code. So go for 19, class 19. Right. So we are in class 19.523. Loss of pre-stress due to relaxation of steel. Okay. Right. So the relaxation loss is going to depend on type of steel, initial stress, age, temperature. Therefore, shall be determined from experiments, and when experimental values are not available, then you can read it from table 6. Okay, so pre-stressing, loss of pre-stress due to relaxation is measured or will be told as at 1000 hours at 20 degrees centigrade plus or minus 2. Okay, so this table I have presented to you, that you can see here. So normal relaxation steel you shall consider unless otherwise mentioned in the problem that the steel is low relaxation steel is used in the pre-stressing. So there is a type of steel called low relaxation steel also available. So to reduce the relaxation loss, the manufacturing of steel can happen, and that is this much. Only half of stress is lost when you use low relaxation steel. So we generally go for, if no such information is there, we generally read this one. Okay, normal relaxation, right? So column number 3 is very general. Column number 4 is a special steel, what is called low relaxation steel. Okay? And this is in terms of percentage: 3%, 5%, 8%, and 0 up to 50% of stress. So anything below 500, if you take 1000 megapascal as a characteristic strength of steel, anything from 0 to 500 relaxation loss will not be there at all. And if you induce the stress beyond 50% to 60, 70, 80%, that is going to be as you increase the initial stress, the relaxation loss is also going to be increased, and the maximum is 8%. Okay, and it can be read like this. And if you have any value in between, you can always interpolate between the values for other values. Okay, right. And for long-term relaxation losses, this is only at 1,000 hours. For long-term relaxation losses, the values of relaxation losses given in table 6 may be multiplied by 3. So 3 times you can multiply if you want the relaxation losses to uh, higher number of days. Okay, right. So this is only at 1,000 hours mentioned here. Okay, so anything beyond long term is only 1,000 hours. So if you want long term losses to be found due to relaxation, so this values shall be multiplied by 3, which means almost 25% of the stress is also is the 8 threes. 24% is the maximum loss that can happen if you stress the tendon to 80% of its characteristic strength. So this is to read how to read the tabular values given in IS code. Okay, and you have some more notes mentioned here that also can be uh, gone through wherever there are it is necessary. Okay, okay. So reading the IS code is always of first priority. That when you are designing any such members, you shall follow IS code in total, right? Okay, thank you. We'll go for the other losses to talk about. The only loss left over is the frictional loss that we'll take up in the next class. Okay.